Have you ever seen the ground proximity warning systems that are used in full-scale aircraft?
Terrain, pull up.
And do you want something like that in your own remote control plane? Well, stick around because we're going to go through the parts required, the build, the code, the installation, the failures, and of course, the test flight. Now here's everything you're going to need for this mod. An Arduino Nano, a JST connector, both female and male, a 4-pin connector which will connect you to your HCSR04 ultrasonic sensor, an LED, I went with a 1.8mm red LED, a power source, which means you're going to have a female XT90 connector or whatever power source connector you want, as well as some pretty cool 3D printed parts that you can find on our Thingiverse account. In this video, I'm only going to give a high-level overview of what I went through, but if you want to follow along and do this yourself, we live streamed the entire build process from start to finish, so I'll link that in the description as well as up in the corner, so if you want to follow along, that's the way to do it. We're going to start things off with the Arduino Nano. I went with this board because it's not only can handle a 2-cell battery, which is what I wanted to power it with, but it's also able to handle the 5 volts that this HCSR04 ultrasonic sensor needs, as well as giving enough power to the LED. So as you can see, there's quite a lot of wiring going on, but if you take a look at this diagram, it should make it really easy. And the only thing I'm going to add is that the power wire, as you can see, comes from these bottom 2 pads, which are going to go right there. Other than that, it should be all right here. You can also find a link to this really nice diagram in the description. Next step is to attach your LED to the male side of the JST connector, and then you can plug it in. In my case, I wanted to add it into this cockpit I already have installed. So as you can see, I've got my JST connector here, and it goes into the furthest right port on the side. For a quick overview on the code, you can go to the Inverted Aviators RC repo on GitHub and download this file in order to upload it onto your Arduino. For starters, we can go and look at the default values for these pins. As you can see, we are just setting the constant for the LED pin, the trigger pin, and the echo pin, so the board knows where to look to find all these values. And we're also setting the number of readings to average, which means the system takes 5 measurements and averages them in order to improve accuracy. Then we're going to set up the board and initialize a serial communication in order to debug easier, which is just more for the computer side, not for the actual flying. But then we're going to set up the pin modes. The LED pin is an output which controls the LED, the trigger pin is an output which sends pulses, and the echo pin is an input which receives reflections. We're then going to print information to the serial monitor, which again is just for debugging. Then we have our big loop which is going to run constantly as this board is powered up. We're going to start by initializing the total duration to store the sum of multiple ultrasonic sensor readings, so as this loop goes, we can slowly accumulate the values. We are then going to loop 5 times, which is again the amount of times we set for the board to read before it makes any calculations, and it's going to send an ultrasonic pulse, measure the time it takes for the sound wave to bounce back, add each reading to the total duration. It's going to wait 10 milliseconds before taking the next reading to avoid any interference. We're then going to calculate the average duration, and lastly we're going to display the results in the serial monitor if you want to make sure that everything is working on your computer before you go out to the field. This section right here will print the average duration in microseconds to the serial monitor. Lastly, we're going to control the LED based on distance. If the average duration is less than 10,000 microseconds, it assumes the object is close and it turns the LED on, otherwise it keeps the LED off. Now you can change this value if you want it to look a little bit further or a little bit closer. I set it to 10,000 because it's about my height, and if the plane's ever that close to the ground, I for sure want that light on. After double checking all of your wires, it's time to install the ultrasonic sensor into your plane. This is really easy, especially if you use a custom 3D printed mount for the sensor, because all you have to do is find a square that's facing as straight down as possible and cut a hole into the bottom of your plane. All I then did was add some hot glue, and the sensor fits in really, really well. Next, you're going to want to route your ultrasonic sensor wires into the fuselage of your plane, and then once it's in there, install your LED. In this case, I'm putting it into the dashboard of the cockpit just to make sure it's inside the view of your FPV camera. Next is just to solder in the JST wires onto your LED, and then you should be good to go. And lastly, installation into your plane is super easy. I took our Arduino Nano and put it into our 3D printed case and added the top lid for a little bit of extra protection. Then I'm going to take a double-sided piece of tape, stick it right on the back, and peel off the non-sticky side. And we can just click it into our plane wherever it fits best. Then we have these extra wires hanging out, and that's to connect to our battery, our LED, as well as our ultrasonic sensor. So what I like to do is have a 2-cell battery up here, and I can plug that into our board when we need to. So I'll install the battery there, and then we'll have the LED coming to this JST connector, which is poking out through the top. So that's also an easy plug-in. And lastly, this ultrasonic sensor would normally be in the wing, but for the sake of the demonstration, I left it out. But this wire is going to route up through the bottom and plug into that 4-pin connector. And just like that, we can give this a little test by plugging in our board into our 2-cell battery. And we can immediately see that this red light turns on in the cockpit, and that's because it is reading something that's very close. Now, if we turn it and point it away from anything, we can see that the LED turns off when it doesn't detect anything. Then we move it back, you can see stuff, and just like that, that's how the ultrasonic sensor is supposed to work. Now let me make something clear right off the bat. If you're designing something and trying to progress and make something cool and things aren't going well, those are not failures. They are opportunities to learn and grow so you can move on in the hobby. That being said, I did not learn twice with these Arduino Nano 33 IoTs, and I didn't do enough research. These boards have 3.3 volt logic circuits in order to get all the peripheral the right amount of power. This ultrasonic sensor has a 5 volt necessity. This board wasn't setting enough power, and in result, it was getting the wrong amount of voltage back, which ended up frying both of these boards. That's how I eventually figured out to go with the Arduino Nano, is because it had a 5 volt logic circuit, and that's how I eventually got things working. Now I did connect all these up and I actually tried to fly 2 different times. Once I got all the way out to the field and it didn't work right away.
The gear is down. Can you even see that? Oh, I think the blue light's very dim. Sensor just went off. That's questionable. Why did that turn off? So questionable. Why isn't it working? This is so frustrating. Why are you not working now? Why aren't you working? God, can that please work? Why is it not reading any signal? I don't know what's the matter with it. It's getting power. Is it fried? What's the matter? Please turn on. Can you please just start working? Like, the LED has a resistor. Of course, it all works at home, and once I get out here, it stops. Like, what's the issue? Alright, whatever.
And the second time, I thought I fixed everything up and it worked on the bench, and I took it out to the field and the same exact thing happened. But I didn't give up, I stuck with it, I switched boards, I rewired things, and eventually we got it all working. So now let's take a look at how the first flight went.
Another great day for flying. As you can see, it is windy and cold, but I just wanted to test this landing light. Just want to see, get closer to the ground. Light turns on, you can see that. I was getting close, you know, semi-close, not really that close, but light's turning on because I'm getting close to the ground. You can see it kind of popping up, but that's just the whole goal, is to just say, hey, maybe we should fly higher. See red light. See the indicator, you can see it reflect in the side there. We're getting close to the ground, we should probably pull up. There we go. As you can see, we're on the ground, the red light is on, telling us, hey, we're too low for flying. That's the whole point of the sensor, just to let me know that it's on. It's not perfect, but that's at least part of the project.
There are a few key takeaways that I've learned from this experiment so far. Number one, do your research. There's no reason why I had to burn through 2 of these boards to realize that they needed 5 volt logic circuit and not 3.3, It was just me seeing a board and going, it probably works since they're both branded under the Arduino header. They should work, but in reality, I needed to do more research and figure out what actually worked together rather than just hoping. Number two, the sensors that I chose were due to the limitations I set on myself. I wanted this whole process to be as cheap as possible just to get something into the air and see if it worked, and then from there I can make further modifications. I went with this HC SR04 ultrasonic sensor because it's super cheap. You can get a pack of 3 of them for just like 10 bucks, connect it up to the board, and it's good to go. With these ultrasonic sensors, these send out sound waves and measure how long it takes these sound waves to bounce back. They're great for obstacle detection, and they work in total darkness, which is great when I'm flying late at night. But since they use sound, soft materials like cloth or foam can absorb these waves, making them unreliable in some cases, and they're also not the fastest because sound travels slower than light. I think that was the reason why when I was getting close to land, sometimes that light would flicker on and off, is that I was flying over snow and I was flying fast, so there was vibrations in the plane, which I think messed up the sensor and it wouldn't correctly read back the sound pulse it sent out. So while it was super cheap and it fit really well into the plane because it's super light and it only needs 5 volts to make the whole thing work, I think I did pay for it in a sense that the accuracy wasn't all there and the light sometimes flickered on and off. Now, there are other options for sensors that I could have used. There are infrared sensors, and instead of sound, they use infrared light to detect objects. They're super fast and really precise even at short distances, but they don't play well with sunlight or other reflective surfaces. Too much light and they get confused, and if an object is too shiny, the reading might be off. So that goes back to the snow I'm flying over. If I want to fly during the day, these infrared sensors might not be able to see the ground at all, and I might do even worse than a cheap ultrasonic sensor. Now, if you want high precision and long range, LiDAR is king because it shoots out laser pulses and measures the time it takes them to return. It's super accurate even at long distances, which would be awesome in a plane because then I can really tell. I can make the light turn on a little bit more if I'm getting closer. And since I only have about a 2-meter distance with this ultrasonic sensor, having an even longer distance would be awesome, but all this extra distance and accuracy comes at a cost, as these LiDAR sensors are usually more expensive and need more processing power to handle the data. Now, I could just put a bigger battery with this whole system in order to handle the LiDAR sensor, but I think it's super convenient that this is such a tiny sensor. It's lightweight, it doesn't need a whole lot of computational power, and I can even probably run this whole system from the balance lead of the normal battery that powers the plane, which is again why I went with this cheap and light ultrasonic sensor. Now, I'm not throwing in the towel on this project yet, and I will come back to it to make more upgrades and modifications, so let me know in the comments what sensors I should use, what different things I should do about this. If you like the case, let me know. Everything can be found on our Thingiverse account, at least the cases, and then I will also put up on the shop this whole system. If you want to buy and you don't have the ability to print the parts yourself, you'll have the ability to buy the parts or the whole thing, whatever you want. It'll be up on our shop, so make sure to check that out. I also want to give a quick shout out to our members so far. Thank you, Glenn. You are the one and only member, which is awesome. Thank you so much. If you do want to join the YouTube membership, it's just $1 a month and you get early access to our videos, and it turns around and helps us make more cool things, fly more planes, bring more content to the channel. So if you've been enjoying the videos, make sure to subscribe, but also if you want to join the membership, it would be awesome. It would help us out so much. But that's been the ultrasonic sensor on the plane. Thank you so much for watching. Stick around if you want more content like this. And thanks again for watching.